We are given this problem. It's based off of Bode diagram. We're not going to actually plot. We are going to use straight line approximation conventions, and these can be found in the notes linked below the like button. It is a little bit confusing, so that's why we're going over them here. It's in chapter 14, Bode diagrams. It's the first section of chapter 14. So when we look at this, what we need to note is the zeros and the poles. That's the first thing we're going to do. Well, we see that we have an S right here, but we have nothing with it, and this is equivalent to this. So that means our Z is 0. And our P1 and B2, we have a positive lower value and a positive higher value. Our positive lower is 3, our positive higher is 100, so we're going to have 3 and 100. Now, the rest of this is a little bit confusing in the notes, so it's good that we're going over it here. Gain K in dB after putting in standard form is the following. We know that K naught is equal to our K, or the constant out front, times our 0, if we have one, since we don't here, we're not putting anything here. And this is being divided by our P1 and P2. Our P1 and P2 are going to be just 3 times 100. And our K is the constant out front. It's just 900. So we're essentially just going to have 900 over the poles. And this is going to give us a K naught equal to 3. And with a K naught equal to 3, we are not done yet. We need to plug this in to our 20 log base 10, and then we'll have our K naught inside of here. And then plugging this into a calculator, remember K naught is equal to 3, we are going to get approximately 9.54 dB. Now we're going to look at D and E. Both are very similar, but also quite different. So these again can be found in the notes, but it is a little confusing. So for part D, what we're going to have is our transfer function. We're given it here. We're just going to replace our s's with j omegas. So s is equal to j omega, and we know we can do this. So we are going to have h j omega, and this is going to be equal to, we are going to have our 900 times nothing, because, well, we have our s, but after the s, we're just going to have nothing after that, so we just have j omega. Now, beneath this, we are going to have our j omega plus 3, and then we are also going to have our j omega plus 100. Now, we're given this right here, but we're not substituting the entire j omega with this 30, just the omega part. So inside of here, we are going to have a 30 times j. Inside of here, we'll have a 30 times j, and then also inside of here, we'll have a 30 times j. And now we need to convert this into the polar form. That way we can divide these two together, or we can just plug into a calculator, but a super simple way is just to, you can do either or, really. But I'm just going to, since I've done so many plugging into calculators, the polar form here. So if we rewrite this out, it's just going to be the square root, because we're looking at magnitude for here, of our imaginary number plus our real number squared. And then below this, we're going to do the same thing. Since these are individual parts, we're going to have to do them individually. So we'll do this part, and then we will do this part as well. So that is going to give us approximately 8.577 once we have all of this worked out. Keep in mind that our j omega is squared, so the j, being an imaginary number, is just going to be a -1, but since it's squared, we don't really include the j inside of it, and we've gone over that in the previous problems and theory and stuff like that. But plugging this into a calculator, the square root and the squared are going to cancel out because we don't need to worry about this 0 here. So we're going to basically have a 90 times 30. And then in the denominator, we're going to have the square root of our 30 squared plus 9, or 3 squared. And then we're going to multiply this by the square root of 30 squared plus 100 squared. And again, this will give us 8.577. We are not done yet, though. We need to plug this into our log, just as we've done up here. So this is going to be 20 log base 10, where you have 8.577. And this is going to give us approximately 19 dB. Now we need to solve for our phase angle. For our phase angle, when omega is equal to 100 rads per second, we are going to take 90 degrees. From this, we are going to subtract tangent -1 of our, because we only have poles and not zeros, we're not going to worry about the zeros. If we did have zeros, we would add them instead of subtract them. We are going to have our 100 over 3, and then we are going to have minus tangent -1, and then, oh, the reason why, by the way, we have this 100 is because of the j omega. So let me actually rewrite this. We have tangent -1, and then we are going to have, if I really rewrite this just so it's bare bones, we are going to have j omega over our p1 minus tangent -1, and then we have j omega over our p2. And then remember, the 0 would be just at plus tangent -1, but we don't have a 0 here, so we're not worried about that. We know that our p1 is 3. We know that our p2 is just going to be 100, or I'm sorry, not one, oh yeah, it is 100. And then this top part right here is just 100. Don't worry about the j, we're not concerned about that here. We know that when we take the polar form with the magnitude up here and with the angle down here, we don't plug in the j for the imaginary number, and this is just going to be 100. So we're going to have 90 minus tangent -1 of 100 over 3, and then minus tangent -1 of 100 over 100. This is going to give us about 90 degrees minus 88 degrees minus 45 degrees. And so when we combine all this together, we are going to get the approximate value of -45 degrees. So we have -45 degrees here, and that's how you would look at this problem and kind of go about solving something even similar to it.